This is Lab 5, The Falling Slinky by Alexis Hernandez Celis. The purpose of this lab was to replicate the motion of a slinky utilizing fundamental physics principles in the computational model, and the overall results of the lab were that we were able to indeed replicate the motion of a slinky. To do this, our code relied on three main equations functioning together. First, we had the constant downward pull of gravity, which is the force of gravity is equal to negative mass times gravity times the vector. And working against this is Hooke's law for spring force, which is the spring force is equal to negative k times s, which dictates how hard the coil pulls on each other. Finally, we bring them together using Newton's second law, or the momentum principle, which is net force is equal to the change in momentum over the change in time. By calculating the net force of gravity and tension, we can iteratively update the velocity and position of the slinky over time. Here's a quick demonstration. All right, moving on to the computational model. To build our computational model, we first define our system and its surrounding. The system is a slinky itself, which I modeled using 40 discrete point masses, while the surrounding consisted of the Earth providing gravity. Now, looking at our key parameters, each mass segment has a mass of 0.01 kilograms, and spring stiffness is 150 newtons over meters. And the most critical part of our initial setup is establishing perfect static equilibrium. In the initial parameters, the stretch between each discrete mass is pre-calculated so that the upward tension perfectly balances the downward weight below it. Now we move on to the main computational loop. We step through time using a very small iterative of delta t of 0.0001 seconds, and inside this loop, we calculate the net force acting on every single mass segment. For each mass, we calculate downward gravity, the upward spring force from the mass above it, the downward spring force from the mass below it, and a damping force to simulate energy loss. Once the net force was determined for a segment, we applied the momentum principle to update its velocity, and then used that to update its position. And the code itself also included logic to handle the collision of the coils stacking together. This code generates the position versus time graph you see here. The blue line represents the top mass, while the red line represents the bottom mass. And then we can notice that at time 0, the blue line drops immediately with a steep curve, while the red line remains perfectly flat, indicating that there's zero change in its position. And the vertical dashed line shows the exact moment of collision, and the graph mathematically proves that the bottom mass does not begin to fall until the top mass physically reaches it. Now, watching the visual output of our VPython model, here's a quick demonstration. And then one more time. We can confirm that three distinct observations. Observation 1 was that the top section of the slinky accelerates downwards rapidly upon release. Observation 2 was that the bottom mass remains completely stationary, suspended in mid-air. And observation 3, that the bottom mass only begins to descend after the collapse top section collides with it. So physically, why does the bottom stay still? Before the drop, the upward tension equals the downward gravity, meaning the net force is 0. When the top is released, it immediately loses its upward tension and falls. However, this change in tension creates a compression wave that travels downward through the coil. It takes physical time for that wave to reach the bottom, and until that wave arrives, the bottom mass still experiences the exact same upward tension and balancing gravity. Therefore, the net force remains 0, and its acceleration is also 0. All right, finally, in conclusion, our computational model successfully did replicate the real world phenomenon, proving that the bottom of a drop slinky does remain motionless until the change in tension propagates throughout the spring. We saw in both the physically observed model and the computationally calculated model that they were indeed similar. They did indeed follow similar heights, similar trajectories. But our model did have a couple of limitations. It models discrete point masses instead of continuous physical mass. It also uses a simplified damping coefficient, and it didn't account for the 3D swing of the spring. But despite these limitations, it does serve as an accurate representation of the system's core physics, which does indeed conclude this lab.